Hi everyone and welcome back. So we're going to continue our discussion on simple harmonic motion, and we're going to start off by talking about what the conditions are that are required for simple harmonic motion. I think after having watched the last video, it should be pretty evident to you what these conditions are. So condition number one, your oscillation or your vibration has to be about a fixed point. And what you also have is that the acceleration is always going to be directed towards that fixed point. Remember, we were saying that the acceleration is in the opposite direction to the direction of displacement. Well, quite simply put, the acceleration is directed towards that fixed point. And that fixed point obviously happens to be the mean position or the equilibrium position. Finally, the magnitude of the acceleration is going to be proportional to the displacement from that fixed point. And you know this because the acceleration is always going to be increasing the farther away you get from that fixed point. And that's why you're able to bring something to a stop at a maximum displacement point, and then the pendulum or whatever it is swings back to the mean position that it started off at. So now if we remember the graphs that we made for simple harmonic motion, you could see that they were of the form of a sine graph or a cosine graph. Well, the conditions for simple harmonic motion give us this proportionality equation, which is that acceleration is proportional to negative x, where a is the acceleration and x is the displacement, right? And the minus sign comes in because the acceleration is in the opposite direction of the displacement. So you need some kind of a proportionality constant to make an equation to happen, right? Out of this. So it has to be negative, some kind of proportionality constant times x. And what we found experimentally is we have the angular frequency omega squared. That is a very elegant solution, basically, to that proportionality constant. So this is the critical equation. This describes simple harmonic motion. And the graphs that we came up with on in our previous video for the displacement time and the velocity time and the acceleration time graphs, they are quite simply the solutions to this equation. And the precise equations that they represent are as follows. So you don't need to know how this equation was derived precisely, but think of it as in more of an intuitive sense. So what happens when time t is equal to 0? Well, when time t is equal to 0, this guy right here is going to be 0, won't it, right? So if that happens, then this whole thing at t equals 0, x will become 0, right? So this also leads us to an interesting kind of way of looking at it. What happens when x equals x naught, right? So when x equals x naught, let's write this out. At x equals x naught, basically the equation becomes x naught divided by x naught is equal to sine of omega t, or it's equal to 1. Now, when does the sine function reach a value of 1? It reaches it at 90 degrees or pi by 2 radians, right? So if I was to do an inverse sine of this, omega t has to be equal to pi by 2, right? And what is t equals pi divided by 2 omega? Does this ring a bell? What could this be? This is the time period. Because if you remember, we said that the angular frequency is equal to 2 pi upon t. So if you do a little bit of arithmetic, algebra, you will be able to see that once you have reached the time period t, when that has occurred, you have hit maximum displacement. So that's a really elegant way of showing, when you reach x naught. You reach x naught at time equals capital T. Or perhaps a more accurate way of saying this is that your time period t is the amount of time that needs to elapse before you reach maximum displacement. So if the displacement equation is x equals x naught sine of omega t, well, what is dx by dt? If I take the derivative of x with respect to t, It's simply v, isn't it? It's v equals dx by dt, which is equal to, well, what's going to happen here? What's a constant? X naught is a constant, and inside this function you have omega t. So omega is going to have to come out. It becomes omega t, omega out here. And then what happens to sine omega t? What's the derivative of sine omega t? Well, it's just going to be cos omega t. And then similarly, what is acceleration? Acceleration is equal to dv by dt. So if we plot this out, once again, x naught is a constant, it'll stay out there. This omega is going to come back out again here, so this makes it x omega squared. And then what is the derivative of cosine? It's negative sine, so there's going to be negative function out there, negative sine omega t. So that basically gets us where we need to go. These are the equations that represent simple harmonic motion. I would also like you to just do one thing for me. Bear with me as I go through this. Let's take a and divide it by x. Acceleration divided by x. What happens right there? You've got the equation right there in front of you, right? It's negative x naught omega squared sine omega t divided by x naught sine omega t. So the sine function cancels out, the x naught cancels out, we're just left with negative omega squared, or a is equal to negative omega squared x, which is exactly what we were looking at 2 minutes ago on the previous slide. So this, guys, is how we look at simple harmonic motion as a whole. So if you now want to try and calculate the velocity of a vibrating body, how would you go about doing it? And I should say velocity of a vibrating body at any point in the acceleration, in the oscillation. How would you calculate that? Well, quite simply, what you would end up using is v equals plus or minus omega. It's plus or minus because it can be in one direction or the other, right? And you would take x naught squared minus x squared. So whatever the position is at that time, and whatever the maximum displacement position is, you have to subtract the squares from each other, take a square root, and multiply it by the angular frequency. And this also allows us to say that when your displacement is 0, when this guy is equal to 0, you have the maximum possible velocity at that time. Do not worry about how this equation was derived, I would say, for the purposes of our studies here. But let's look at an example to show how we can how we can use this equation. So let's say we have a mass at the end of a spring and it's oscillating, right? It's moving up and down. And the oscillation period is 1.6 seconds and the amplitude of the oscillation is 2.4 centimeters. So how would you calculate omega? Well, omega, the angular frequency, I mean, you know what the frequency is, right? It's 1 upon t. So it's going to be 1 upon 1.6 hertz, whatever that works out to be. And what is omega going to be? Well, omega, we know the equation is 2 times pi times f, or 2 times pi divided by t. So if you work all of that out, the angular frequency, remember, it's in radians. It's going to be radians per second. If you don't know why it's in radians, please refer back to the videos on circular motion. And then you have the question, what's the maximum speed that this mass is oscillating at, right? So our V max is at x equals 0, right? So, which is equal to omega x naught, which is equal to 3.9 times 2.4, and that gives us 9.4 centimeters per second. So let's keep going. We can also try and calculate the acceleration here. So acceleration is going to be negative omega squared x. So now you know what omega is, and you know what the maximum acceleration is going to be. in order to make that happen, go back and remember, when does the maximum acceleration happen? Well, maximum acceleration happens when you are at the maximum displacement point. So we'll have to go with the amplitude there, x naught. So this guy then becomes, if you do the arithmetic on that, this one becomes 37 centimeters per second per second. And what else could we learn from this system? Well, one other thing that we can learn from this system is what is, let's say, what's the speed of this particle at a certain point, right? So let's say I want to know speed at a displacement from its equilibrium position of 0.6 centimeters. And the way you would follow through on that is going to be omega x naught squared minus x squared, and then omega is going to be 3.9 times the square root of 2.4 squared minus 0.6 squared, and that works out to be 9.1 centimeters per second. So folks, that brings us to the end of this video. Let's take a look in the next video in terms of energy in simple harmonic motion. So we've been talking about, speed and acceleration and displacement. So let's talk a little bit about what happens with energy in simple harmonic motion in the next video. So I'll see you there. Thank you.